So today on the bench we are going to take a look at this power supply that is from a Cannonscan 9000F, and this is not the Mark II version. This is actually the Mark I version, because the Mark II version has an external plug back to all I know. So yeah, but so this power supply is having a plastic case that's like 2.5 millimeters thick, which is really thick. I think you can drive it over it with a car without it breaking all that much. So overkill to say the least. Internally, it's actually quite a nice design because we have the AC inlet, we have a small capacitor over here, we have a fuse, we have a common mode choke before it going into the bridge rectifier. Then we have our main filter cap, and over here we have actually the nicest feature, which is the NTC thermistor, because it has over temperature detection and it will turn off. Down here we have a small suppression capacitor, and then we have our optocoupler, our bulk storage on our output, and then we have this small other common mode choke, which is quite nice. Then we have our main transistor running the show, or it's probably not running the show, but it's doing the business. And this is from a company called AUK. I have never heard of them before. The transistor's name is STKO460P, which is not a name you just roll off the tongue per se. It's a 600 volt rated transistor. It has a VGS of 30 volts, which is actually quite high. It has a threshold voltage of 2 to 4 volts, depending on how it's manufactured. It can take 4 amps or 16 amps peak, which is kind of good. Like, it's not a bad transistor. It's not super good either, it's kind of decent. Good enough for the application. Here's another view on our board, and unlike our main transistor here, which is from some company we have never known of or never heard of, this is a Nippon Chemicon capacitor, which is 400 volts rated, 82 microfarads. It's actually quite good. And then we have a bridge rectifier, which is actually using a configuration I haven't really seen that many times before, because it has one connection going up like this and another connection going over like that. And then you have the negative rail sitting there, and then you have the positive rail sitting here. Quite nice design. Over here you have the small dip arrows stating what direction this board has traveled through. We can also see a small mistake made by the manufacturer in this view, which is the NTC thermistor. It's glued onto the tape instead of actually to the transformer. So that's nice, because the tape is highly thermally conductive. Everyone knows that tape is the best thermal conductor in the world. Or if we aren't ironic and joking, we can actually say that this is quite horrid, because now the NTC thermistor is barely going to do its job. And secondly, I would have actually placed the NTC thermistor somewhere like over here, next to our transistor and next to our transformer, because over here is likely where we have the hottest components. Because we have the big freaking transformer sitting here, and we have the big freaking transistor sitting there. It's quite a good location to place it, but that's just my opinion. Now we can take a look at the underside of the board, where we have the next freaking thing running the show, which is the actual switch mode power supply chip. So this is an SJ, that's a 6. This is an SJ. 684696, so that wasn't better, 6B, and then it's an LSZ, I think. Yes, an LSZ, which is practically just saying that it is reduction of hazardous substances compliant. And the thing is, they did have enough room on the chip to just write ROS on it instead of LSZ. So that's a bit silly. Next thing we can see is they have a nice acid trap up here. Not that modern manufacturing processes cares much about that. We have our nice bridge rectifier on this side. We have some crud up here. And here we have a nice discharge resistor for the filter capacitor sitting on our AC side, which is quite nice. And then we can notice this thing. Like, what are these two resistors doing? It's a total series resistance of 660k, and it goes from our AC side of our bridge rectifier, then it goes over into the auxiliary side of our switch mode power supply controller. Why it's doing that, I have no clue. And yes, I'm not joking, the datasheet is actually stating that it should do that, and yes, it does go in between there. So I actually suspect that this resistor is supposed to sit over here, because that would make more sense, because most designs have it there, not over on the AC side. The problem with having it over on the AC side is this point here is going to vary between being positive with our full mains voltage or negative with our full mains voltage in reference to this. And this is our, I don't know why they've actually used the earth symbol. They should have used the ground symbol. So yet another mistake inside of this datasheet. Good on Semiconductor, you're doing perfect datasheets. Or this datasheet is freaking perfect. But yeah, because this point is going to have the lowest voltage of these two. So either this point is going to be substantially more negative than this point, or it's going to be substantially more positive than this point. And this is a polarized capacitor, so we can make a small guess of what's going to happen eventually with it. It's not going to be a happy capacitor. We can say that much. So, not really a good design. And the board maker here has just simply followed that and just saying, yeah, the datasheet says to build like that, I'm gonna build like that. And considering their acid trap up here, yeah, I can probably understand that maybe they didn't catch the datasheet. Unlike another switch mode power supply controller from on Semiconductor as well, where they actually have a very nice feature inside of this. So this has a high voltage constant current source, so it pulls down current through here, down out through the VCC and into our capacitor. This resistor is going to drop about 90 to 100 volts, and we're pulling about 10 milliamps, which is quickly going to charge up this capacitor, and then when it reaches a threshold voltage of, I think it's 12 volts, I don't remember, it could be 13 or 14 volts, somewhere around there, then it's going to turn off this, or rather, then it turns this off and starts the whole freaking chip. So practically starts running our transistor. And the advantage here is that we don't have any current flowing through our resistor, and we don't have any power dissipated within a high voltage section, meaning that this doesn't consume any power, meaning that our power consumption of this whole switch mode power supply is actually going to be quite a bit better. Unlike the other design where we are going to have a resistor here that's always going to be dissipating power regardless. So, like, this is going to dissipate power even if we have the auxiliary winding giving us plenty of power. So this is just redundant. And having redundant power sources that, by the way, is just resistively dissipating most of the voltage across them isn't all that energy efficient. So yeah. And if we go and check the data sheets for these two components, then we can start to see that the SJ6846B with the LSZ version, which is Rust compliant, it states that it's a highly integrated green mode PWM controller. And yeah, green mode is partly just saying it's eco-friendly, it's high efficiency, it's a good design in other words. And yeah, I wouldn't really say that having a resistor just dissipating power continuously is a good design when ON Semiconductor has a superior chip in terms of passive power consumption. So that's one thing. Though I do like the NTC resistor because that's something that the NCP does not have. So I would like to see the NCP with, or to be honest, I would really like to see a chip like the NCP but with like dual phase outputs, because that would be really nice, because then you can make a very ripple free output. But I haven't found any mains voltage power supplies with dual phase capability ever, so that would be a really nice feature. And especially also having an NTC resistor or two would also be quite nice. If you have two phases, it's logical to have two NTC resistors, at least from my point of view. I would also like it to have like high side sensing, because that's more logical, to be honest, but that's just my reference or my preference. Then this is also having this RI pin, which is a reference setting. I don't know why they call it RI when they're also saying reference setting. RS would be more logical, but I'm not in charge of their naming schemes. But practically it's a pin where you have a resistor setting the oscillation, or rather the switching frequency of the device. And the NCP simply fixes this by having 3 different versions of the chip. So it's neither here nor there. It's 2 different ways of doing it, and I don't really care. This here is quite nice because you don't need an additional resistor on your board. Though I think if you just leave this resistor on, I think it's just going to run at its highest or lowest. I don't remember. It's going to run at one or the other. Yeah, increases in resistance reduces the switching frequency. So yeah, if you don't have the resistor, it's going to be as slow as possible. So then you know that. So yeah, so it's just 2 different chips, and yeah, you can compare it, switch mode power supply chips until the cows come home. It's not really all that hard. But now we're going to go back to our power supply, because our power supply has even more tricks up its sleeve, because we have this section, which is even more fun, because if we go and take a closer look at it, then we're going to see we have a small transistor down here, we have a transistor here, and we have our optocoupler up here. So this transistor drives our optocoupler through this long path, and then this is going to some resistor over here, and then I think it connects over to this ground plane. So, no, I don't think that's a ground plane. It might be the positive plane. Or, yeah, I think this is the positive. So this is probably the positive plane, because this is the negative plane. And because this is the negative connector, and that's the positive connector. And here we have our common mode choke. So, and then we have this pin, which I have no clue what it's doing, but it's driving our transistor over here through these 2 resistors, driving this, that then jumps over and drives that in some way, shape, or form that's also being driven by this cluster of resistors. So I have no clue what they're doing, but they're doing something. If I would design this power supply, because it has a 32 volt output and can sustain 0.65 amps, it's not really a high powered thing, to be honest. But if I designed this, I would just have 32 volts here on the output continuously. I don't see the problem in that. And if you use the NCP 1203, it's even going to be power efficient. So I have no clue what the designers of this power supply are doing, but they're doing something. And I'm suspecting that the power supply here is broken, or that this chip is the culprit for why it doesn't work. And because this chip is obsolete, I can't easily get a hold of it. Okay, I could probably buy it off of eBay without too much problem, but considering this little fault down here, and yes, I'm just gonna call it a fault because I don't see how it's logical, then yeah, I don't suspect a new chip is gonna last all that long regardless. There is this voltage in. If the but the voltage in goes away and connects up here, and that's like, I don't know what the voltage in is doing. Is it sensing that you have a voltage? Like, if the voltage in would connect to this, and the VDD would connect through a resistor up here, yeah, I wouldn't have given it a second thought, because having a voltage in pin connecting up here would be semi-logical. let's see what the datasheet has to say about that voltage in pin. So if we go over to the datasheet, we go to our highly integrated green mode power supply, and then we go and look at this VN. Line voltage detection. So line voltage detection is used for brownout protection with hysteresis. Constant output power limit of universal AC input range is achieved using this pin. Add a low pass filter. Outline ripple. Okay, yeah. So yeah, it's some form of AC input range detector or something like that. I don't really know what they're doing with it. Maybe this could over power compensation. And then it goes down here, and yeah, it does something. So yeah, I wouldn't be surprised if the voltage in pin is actually supposed to connect here, and this resistor is actually supposed to connect up there. Like, it wouldn't be an all too uncommon mistake for someone to do when laying out a schematics. Like, I've done similar mistakes myself at times without really knowing it, so I don't know how much scrutiny these designs go under, but apparently not sufficient. Or maybe I'm totally misunderstanding what they're doing here, but I don't suspect applying a negative voltage, or rather the reverse polarity, over a polarized capacitor is a smart idea. So, like, even if it's through a resistor, I don't consider it to be a smart idea regardless. So, but that's my stance on it. And now this video has gotten to be really, really long again. But hopefully it has been an interesting video nonetheless, and hopefully it has been at least somewhat informative, or at least somewhat entertaining. So hopefully I might do more of these videos in the future, because it's not too hard to make them, and maybe I get the supply up and running someday. Or I'm probably just gonna build some other 32 volt power source, maybe use like a boost converter or something off of eBay, and see how the scanner reacts to just having a constant 32 volts at its input. Depending on what its weird magical circuitry over here is actually doing. If it turns out that it does something really important and the scanner dies if it doesn't have that additional volt by this additional pin, then, well, I don't really know what Canon is doing at that point. So yeah, I'm just going to try feeding in 32 volts and then being capable of supplying sufficient amount of amps. And if it works, it works. If it doesn't work, it doesn't work. What am I going to do? Can't really do much than that, but experimentation is, after all, a very nice way of learning. So, yeah. Hopefully, see you in the future. So, have a nice day.